Hi, welcome to my channel, JaberTime. I'm gonna go over today the main topics as you could see on the screen: power functions, polynomial functions, end behavior of power functions, intercepts, and turning points. And there is some two interesting graphs that I have for you. Let's get into it. Power functions and polynomial functions. A power function is a function that can be represented in the form f of x equals k times x to the power p, where k and p are real numbers, and k is known as the coefficient. Let's see some examples. Keep those in mind. K and p are real numbers, and we call k the coefficient. Here's quick examples. Those are power functions. If f of x equals 1, I could see it as 1 times x to the power 0. That's called the constant function. If f of x equals x, I could see it as 1 times x to the power 1. That's my k. That's p, k, p, and so on and so on. X to the second will be 1 times x to the second. They all have 1 up front, so I'm not going to keep saying 1. X to the third, cubic function. 1 over x is a little bit different, but if you move it to the top or rewrite this, it's 1 times x to the power negative 1. Real numbers. It's called a reciprocal function. Reciprocal squared function. 1 over x to the second could be written this way. Square root of x, x to the power half. Cubic root of x will be x to the power 1/3. So those are all power functions. Let's take another quick examples separate. Would this be a power function? What do you think? If it's a power function, what is k, what is the coefficient, and what is p as the exponent or the power? If you simplify it, it's 8 times 2 times 4, 8, and you add the exponent here because I have the same base. Think about it this way: x times x, and here I have x times x times x. So it ends up 5 x's multiplied together, which is x to the 5th. That is a power function. That's my k. That's p. K x to the power p. Let's take another example. Do you think this is a power function? Does it look like k times x to the power p? No. This is called a polynomial function. It's not a power function. A power function is just like one term, k x to the power p. So this is not. How about this one? Can I write this as k times x to the power p? No. This is called rational function, not a power function. How about 2 to the x, which is interesting? I think if I see it as x to the power 2, I'll call it the square function, right? Y equals x to the second, which is a parabola, and so on. But not this one. This is not a power function. Let me do some more for it. A power function contains a variable base. The base is the variable raised to a fixed power, x to the power p. So x has to be the base. This function has a constant base. The base is a constant raised to a variable power. That's like the other way around. And this one we call it exponential function, not a power function. Let's take some examples about power functions and how do they behave as graphs. Okay, let's talk about end behavior of power functions. I have these 3 functions on one page. different colors, but they share a lot. Notice that the first one is x to the second, the second one is x to the fourth, and the third one is x to the sixth. 2, 4, 6 are all evens. Even power functions. This is how they look like on the same grid. As x goes to infinity, all the way to the right, f of x goes to infinity, all the way up, in all of them. As x goes to negative infinity, all the way to the left. Usually books don't write it this way, but I'm trying to use the graph and point to the left, as you could see. Still, f of x goes to infinity, up. In short, we write it differently in the book like this. As x approaches positive or negative infinity, going all the way to the right or going all the way to the left, both ways your outputs are going all the way up to infinity. Let's see some more. Power functions with even whole number powers. All these three are power functions with even 2, 4, 6. They have the similar shape. As the power increases, the graphs flatten somewhat near the origin, and they become steeper away from the origin. What do they mean by this? Notice that they all go through 1, 1, this point right here. Why? 1 to the second, 1 to the fourth, 1 to the sixth is all 1, so that's why they go all through the point 1, 1. Once you pass 1, the same thing applies to the left, but I'm not jumping right and left. Let's just focus right here. If you plug in something more than 1, let's say 3, or let's say 5. 5 to the second is 5 times 5. Whatever that number is, I didn't see it on the graph, but somewhere up. 5 to the fourth is 5 times 5 times 5 times 5, even higher. So the blue one is steeper, higher in value at the location 5 compared to the green one. While the red one even is higher, greater in value. Why? Because 5 times 5 times 5 times 5 times 5 times 5. So, once you pass 1, that's regular speed or regular opening x to the second, faster for x to the 4, even faster for x to the 6. They couldn't write it here, it's on the left, x to the 6. So, of course, if you plug in negative 5, same concept, because you're not going to end up with negative. A negative times negative times negative, an even number of numbers is going to end up positive. So that's how even functions, even power functions, they behave. Next, what do they mean by flatten? Look right here between 0 and 1. Imagine if I'm using half. In the green one, it's up here. Half times half is 1/4. Half is 1/4. I could see this as 1 half, that's 1/4. But if you plug in half in the x to the fourth is half times half times half times half, which even is smaller in value. That's why the blue one is below the green in this region. Here, it's going to even be lower in value. Half times half times half times half times half times half, 6 times. So, above 1, greater than 1, green, then blue, then red. This is the other way around. Green going down, blue, then going lower, red. That's exactly what they're saying right here, and I think that should do it for this slide. Here's the odd functions. X to the third, x to the fifth, x to the seventh, they share the odd exponent, odd power functions. This is how they look like. Now the even one goes this way. How come this one odd goes this way? Just like x cubed, we know that earlier. Plug in 1, you get 1. Plug in -1 times -1 times -1 times -1, an odd number of negatives will end up negative. That's why it's not up here, it's down here. As x goes to infinity, f of x goes to infinity also, all the way up. As x goes all the way to the left, f of x goes all the way down. So one goes up, the other one goes down for odd. In short, as x goes to infinity, because books don't write it this way, f of x goes to infinity. As x goes to negative infinity, that means all the way to the left, f of x goes all the way down to negative infinity. These are power functions with odd whole number powers. That's why they are on the same page. They have similar shapes. One goes up, the other one goes down. As the power increases, from x to the third to x to the fifth to x to the seventh, between negative 1 and 1, it flattens. Above 1, below negative 1, it's steeper. X to the seventh is steeper than x to the fifth beyond 1, away from the origin. Okay, that should do it for this one. Here's a summary of power and odd functions, or odd power and even power. If the leading coefficient is being positive, the graph here is going to open up. The odd power will go up this way to the right, will go down to the left. If you have up front a negative sign, or the leading coefficient meaning is negative, instead of going up as even, it's going to open upside down. It's going to be concave down. That's called a reflection about the x-axis, vertical reflection. Look at this one here. We could see the reflection also. This piece is, instead of going up, it's going down. Instead of going down, it's going to be reflected about the x-axis, so it's going to go up. This is how they look like, odd powers. This is how they look like, even power. Just keep that in mind. Even, they both point to the same direction, either up, both ends, or both down. For odd power, one will end up pointing up, the other side will be pointing down, or the other way around. I'm not going to read this again because it was mentioned also, and you could see it. For example, this one here says, as x goes all the way to the right, f of x goes down. We could see it. As x goes all the way to the left, negative infinity means all the way to the left. F of x goes to infinity means all the way up. All right. I think that should do it for this slide. Let's see something different. Polynomial functions. Let n be a non-negative integer. F of x equals the following. I'm not going to read every single detail. Will be called a polynomial function. But I'm using different colors, or mainly highlighting this guy. Because if this is gone, the whole thing will be different. What do I mean by this? For example, if this is 10, and this is 9, 10 minus 1. 10 means that's the degree of the polynomial. 10 means even power. 10 means, with this one being positive, it's going to open up both ways. But if you eliminate this term, you don't have an even power anymore. It's going to be to the 9 if you have that term available, which is going to end up odd power. So this is the main term that's going to tell you the behavior of the graph and more about the graph. All right. So we call this whole thing a sub n times x to the power n the leading term. We call a sub n, which is the front. We used to call it in the power function k by itself, k as the coefficient. Here my coefficient for the polynomial function is a sub n, the leading coefficient. And we call n, which is the highest number that you could see on top of x, the degree of the polynomial. You could be missing some terms here, This could be gone. That's totally fine. You don't have to have a constant. That's totally fine. But the focus is right here. Okay. Let's see some examples, just to give you some support about what is polynomial and how do they behave. 5x to the fourth plus 2x to the third minus x minus 4. That is a polynomial. Yes, it is a polynomial. The leading term is the main term that we care about. Especially if this one is written in order, I could tell which one is the leading term. It's right there, the front one. 5x to the fourth. And if you take your time and graph it on a calculator or using any software, it shows that it opens up both ways to support even. Positive opens up, even, both at the same time, they point up. Another example, 6 is even degree. So it's either both is going to open up or both is going to open down. In this case, it's going to open down because the leading coefficient a sub n is -2. So it's going to open down. And the graph says it, right? We're not discussing too much about the details like how the graph behaves, like curves and so on. We're talking about even and odd and in behavior. It all comes from the leading term. One more. Leading term is 3x to the fifth. That's odd. Odd, one way looks up, one way looks down. Because its leading term is +3, it's going to look like x cubed somehow. So the left side will go down and the right side will go up. One more. A negative odd power polynomial or odd exponent degree. Well, one side goes up, the other side goes down. But why it's the other way around? Because of the -6, the leading coefficient. All right. So it's not like x cubed. It's like -x cubed. When you reflect about the x-axis, it goes the other way around. So think about it this way. Let's practice some more. The leading term, the degree, and the coefficient of the leading term. Here's some examples that I gathered for you. Polynomial, another polynomial, another polynomial. They don't have to be always f of x. They don't have always to be x. Could be t, could be p, could be anything. The leading term will go in the front. The leading coefficient will go here, and the degree will go here. Let's look at the first one. I'm using colors, by the way, to let you stay focused with me. Take a look. This is not written in descending order. What do I mean by descending order? Take a look. These are called descending order, standard way. Cubic, second degree, first degree, constant. So it's kind of like goes down one by one. Here they want to trick you, or they want you to pay enough attention to spot the leading term. And because the leading term is our focus to tell how the graph is going to end up behaving at the ends to the right and left. So here we go. As you can see, I'm using colors right here. So this is our focus, right? Not this one or this one, right? So what's the leading term? It's this guy here. Now, with that in mind, what's the leading coefficient? It's this right here, -4. With that in mind, what is the degree? Which is up here. The degree comes from n. N is the degree. 3. One more. This one is in order. That's fifth, that's third, that's first. It is in order, standard form. Leading term. Leading coefficient. Degree. I know they're both 5s, but I got this 5 from the front and I got this 5 from the top. One more. That's not in order. So our focus not here or here. Our focus is right here. Take a look. That's my leading term. What's my leading coefficient? -1. Not just a negative sign, of course. What's my degree? 3. I think that should do it. Let's move on to different type of examples. Describe the end behavior and determine a possible degree of the polynomial function. Okay, we have to be careful. We have to slow down. So pay attention with me. As x goes to negative infinity, f of x goes to negative infinity. That's what I have here. As x goes to infinity, f of x goes to infinity. Okay, we got that. This graph has the shape of an odd degree power function. You remember evens, both up or both down. So this is odd, something to agree on. That has not been reflected. You know, it's just like x cubed. It's not being reflected. It's not the other way around. Okay, so it's the leading coefficient must be positive, and it's an odd degree polynomial. We don't know if it's third or fourth or fifth. That's not what we're discussing now, but to me it looks like a third degree. Let's move on. Let's talk about intercepts and turning points of a polynomial function. This is called y-intercept. These 3 points are called x-intercepts. This is called a turning point. When you change from increasing to decreasing, when you make a U-turn, a legal U-turn. Of course, you have to make it legal U-turn. An illegal U-turn means you cannot make a U-turn, but you make it. That's an illegal, if that makes sense. This is another U-turn, differently, the other way around. Okay, let's talk about in detail and stay focused. If you notice, I try not to joke around a lot in my videos because my videos are lengthy, 30 minutes and above. And if I keep making jokes, it's going to be like over an hour. I don't think you're going to like it. That's at least why on my YouTube videos, I kind of like stay kind of like more focused and try to stay with the point. So, moving on, the turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing, which makes sense. Increasing to decreasing or from decreasing to increasing. The y-intercept, that's this one right here in our example, is the point at which the function has an input value of 0, which means when your x is 0. So to find the y-intercept, the game is you set x equals 0, because as you are walking on the y-axis, your x is 0, which makes sense. On the other hand, to find the x-intercepts, you're actually setting y equals 0. There is something important, that's why I'm kind of like, compared to these notes, I'm putting it on the side, let's say boxed or framed, because it's important, more important. A polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. Let's think about it. Think of this graph as if it's cubic to the third degree, which is n equals 3. How many turning points do we have? I have 3 pieces of graph, like 1, 2, 3, but you end up with 2 turning points. 3 minus 1, which is 2 turning points. Just to understand what they're talking about here, right? It doesn't have to be 2, but just to get the concept, why, what's 3 and what's 2, and how does it relate from a graph. N degree n, n x-intercepts at most. I said this is a third, looks like a third, right? Think about it. Okay, with 3 roots. 1, 2, 3. If this is a degree 3, I do have 3 roots. I could see them clearly. Okay, I don't want to confuse you by talking more about when it's not 3 and 2 in the same slide, because I have some other slides, and the coming video actually will talk, the coming video will talk about the multiplicity of the roots and the zeros, and how does that affect the graph or describes the graph. Let's move on. Given the polynomial f of x equals x times x minus 2 times x plus 1 times x minus 4, it's already factored because we want to get started. We don't want to spend the time factoring, and we took this in previous videos. So let's focus on some other things instead of just spending time factoring. Determine the y and the x intercept. The y-intercept, we make x equal 0. We put 0 here, 0 here, 0 here. Do the math, it's 8. So the y-intercept is at 0 for x, 8 for y. The x-intercept, we make y equal 0. It's already factored. That tells me that I have 3 options. Either x plus x minus 2 equals 0, which means x equals 2. Or x plus 1 equals 0, which means x equals negative 1. Or x minus 4 equals 0, which means x equals 4. So to write them down, I could write them as ordered pair as 2, 0, 2 for x, 0 for y. Those are x-intercepts. Negative 1, 0, and 4, 0. To support that, here's the graph. It doesn't say graph it, but that's detail about x-intercepts and the y-intercept. Let's move on. What can you conclude about the polynomial represented by the graph shown based on its intercepts and turning points? Do you think this is odd? Do you think this is even? I think it's even. Is it second degree or fourth or sixth? Let's talk about it in terms of what we have here. Well, to look into it, I do have clearly 2 x-intercepts. We have 1 y-intercept, and we have 2 turning points. You see the turning points? Actually 3. 1 here, and 1 here, and 1 here. From decreasing to increasing, from increasing to decreasing, from decreasing to increasing. Okay. The end behavior of the graph tells me that we are dealing with an even degree polynomial. That is clear. The graph has 2 x-intercepts. That's this one here and this one here, suggesting a degree of 2 or higher. Makes sense, right? Could be like x minus whatever that is. I can't use negative 2.5 because I have to confirm. So 2 roots. Think about it this way, like, without looking at these decimals and fractions. If you have it factored as x minus 3 times x minus 5, that's a second degree if you use the distributive property, and the roots are 3 and 5. 2 roots, that's a second degree, right? That's kind of like the normal way we think about it. So as it says right here, the graph has 2 x-intercepts suggesting a degree of 2 or higher. Why 2 or higher? Because it could be like not x minus 3 times x minus 5. It could be x minus 3 times x minus 5 being squared, like x minus 5 times x minus 5, which means a repeated root. But here it's not repeated because it crosses. So at least to stay safe, you can't confirm it's 2. It's 2 or higher. Think about it. And the more skills, the more graphs, you will know more about more details about writing the equation out of the graph. 3 turning points, you remember n minus 1? Suggesting a degree of 4 or higher. So because I have 3 turning points, it can't be second degree. It can't be second. Because second is a U-shape. Correct? Do you remember x to the second, x to the fourth, x to the sixth? That's not a U-shape. That has enough turns, right? Because I have 3 turning points, it has to be more than 3. And we would expect 4. Could be higher, but that's, I think, so clear. Even with the combination of how many intercepts and how many turning points, we are assuming that it's a 4th degree or higher, as 4 or 6 or 8 and so on. That's what we mean. Based on this, it would be reasonable to conclude that the degree is even and at least 4. That should do it for this video. And I'm working on another one, hopefully soon. By tomorrow, I should end up with 2 more videos. One after this one about polynomials and multiplicity. And the one after is about rational functions and the behavior in graphs. I'll see you next time. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.